So let's look at some examples. Here is a graph of the surface z equals xy. It's kind of funny looking surface, but it's a good example for us to figure out where the directional derivatives are. Okay, so first we want to calculate del of z, the gradient of z. And you don't necessarily have to show this part once it's familiar to you, but I'll just show it to you so you can tie everything together. The partial derivative of z with respect to x is y, and the partial derivative of z with respect to y is x. So del of z is just the vector with those things as the components. So it's going to be y comma x. Okay, now as we know, the directional derivative in the direction 1 comma 0 of z is just going to be the dot product of 1 comma 0 with this gradient. And it actually is just the partial derivative of z with respect to x, which is y. And the directional derivative in the direction 0 comma 1 with z is the partial derivative of z with respect to y, it's the second component, is y. Okay, now let's look at the unit vector that I said we were going to be using in the examples, which is 3/5 comma 4/5. The directional derivative in that direction of z. So we actually have to do this. We're going to take the gradient, which is y comma x, dotted with 3/5 comma 4/5. And that is going to be 3/5 y plus 4/5 x. What does that mean? That almost makes me want to graph a plane, but that's not actually helpful here. So this means at any point x comma y, if I try to walk in the direction 3/5 comma 4/5, then this is the steepness I'm going to encounter. So it's not very useful as a general function. It's more useful at a point. So what's more useful is the directional derivative of 3/5 comma 4/5 of z evaluated at the point 1 comma 2. What's that going to mean? That's going to mean I walk to the point 1 comma 2. So let me look at the graph. Here is the x-axis, y-axis, and z-axis. So I'm going to the point 1 comma 2, 1 comma 2, and then go up to the surface, so there. And then I'm going to walk in the direction 3/5 comma 4/5, so more in the y than the x. So I'm going to walk in that direction. It looks like I'm going to be going uphill. And this value is going to answer the question, how much uphill? Okay, so we've already calculated it in general, so I just have to plug in 1 comma 2. So 3/5 times 2 plus 4/5 times 1, that's going to be 6/5 plus 4/5 is 10/5, which is 2. Okay, so that means right at this point, for every unit I walk in the direction 3/5 comma 4/5, I'm going up 2 in the z direction. That's what that 2 means. So it's kind of tricky. There's 2 points you plug in. There's your position and then the direction you're going. And you need both of those before you get a numerical value for the directional derivative. You could also have plugged in the other way first. You could have calculated del of z evaluated at 1 comma 2. Remember, del of z was y comma x. So del of z evaluated at 1 comma 2 is 2 comma 1. What does that mean? That means if I stand at 1 comma 2, if I walk in the x direction, I'm going up by 2. And if I walk in the y direction, I'm only going up by 1. And so walking in this other direction, I might be going up some different value. And then what does that tell us, or what does that help us calculate? Well, we said in the previous video, the del can help us calculate what direction we walk in for maximum and minimum steepness. So let's calculate the unit vector that goes in the same direction as this. Well, we know that the magnitude of 2 comma 1 is the root of 2 squared plus 1 squared, which is 5. So the unit vector going in that direction is 2 over root 5 comma 1 over root 5. So it means at the point 1, comma 2. 1, comma 2 is what I get from here. Walk in the direction 2 over root 5, comma 1 over root 5 for maximum steepness. If I want to find the fastest way to go up the mountain, I go in that direction. And then I could walk in the opposite direction. So negatives. Negative 2 over root 5, comma, negative 1 over root 5 for max steepness downhill. How fast can I go down the mountain? Let's just look on the picture where that is. So I'm going, how big is that, by the way? 2 over root 5, comma 1 over root 5. Okay, so more in the x direction, but not completely. So this is the maximum steepness, and if I go the opposite way, I'm going the maximum downhill. And then we also said in the previous video, because of this dot product thing for directional derivatives, if I go orthogonal to this vector, I'm at 0 steepness. So if I walk in, actually let's switch colors, go up here. If I walk in, and I could make this a unit vector or not, but like let me just make one whose dot product with that vector is 0. So 1 comma negative 2. That'll give me 0 gradient, or 0 directional derivative. And what that means is that's a level curve. So let's see where I am. I'm here. If I walk in the direction 1 comma negative 2. So we're going 1 in the x, negative 2 in the y. So if I walk kind of this way, it's a little bit tough to visualize, but maybe that's a level curve. So including from that point going 1 comma negative 2, I'm not changing heights on the graph, and the level curve probably goes over this way. So we could calculate other ones. But those should all agree with the level curves of the graph.